everyone, welcome to this lecture on the subject of VLSI design. This is lecture number 6 on the topic of inductance in interconnects, skin effect and some RC models. Okay. So, let us start. Till now we have started this particular unit. The main theme of this unit is to study delays in interconnects, which are the wires which connect different parts in your integrated circuit. So, you have understood about resistance and capacitance in interconnects. Today, we want to discuss something more, which is the inductance which might exist in integrated circuits. So, most of the modern VLSI design tools, they take into account the resistance and capacitance associated with the wires and tend to ignore sometimes the inductance which may be involved. This is particularly the reason being that in some of the high speed applications only the inductive reactance tends to be more dominant, and for low to mid range frequencies the inductance tend to be not play a very important role in ICs. Okay. So, you probably know about resistance, which is dependent upon the dimensions, capacitance which is dependent also on the geometry and also dependent upon how much is the distance between the wire with each other or between a wire and the substrate. Okay. So, these are the two of the parameters, the third being inductance, which we are discussing today. So, let us try to get some of the basics right first. Inductance by itself is a property, is a characteristic of an conductor, which basically tells us how much back EMF or electromotive force it is going to generate when it is subjected to some kind of a electric current. Okay. So, we already know that when current is made to flow through an electrical conductor, it generates a magnetic field. The direction of this magnetic field can be understood by the right hand thumb rule. So, if the thumb is the conductor, the direction of the fingers basically tell you the direction of the magnetic field. Now, this magnetic field develops or tries to oppose the source which produced it. Okay. So, the source which produced it was the level of current which was passed through the conductor and it produced a magnetic field. So, the magnetic field now tends to, in an opposite reaction, develops a back EMF, okay, which tends to oppose the amount of current. Okay. Now, if the level of current changes, it will change the magnitude of magnetic field, okay, and hence the voltage which it is producing, the back EMF which it is producing, that is also going to change with respect to the rate of change of current. Okay. So, the back EMF generated or the potential developed or the voltage developed is directly proportional to the rate of change of current, and this proportionality constant is basically the inductance. So, the equation which we discuss here is V, the voltage developed, equal to L d I by dt. Okay. So, now this is the phenomena of inductance, this is the property of inductance. Now, how and why is it important in an integrated circuit? So, as we have seen that the scaling down has happened on a very large scale, the circuit density has gone up frequently and significantly. So, because of this, the number of interconnects, the density of the wires which connects say part A or point A to point B in an IC, that has also gone up. So, the density of interconnects is also very high. It is possible that the wire which connects one part of the circuit, one part of the integrated circuit to another part of integrated circuit, it may not travel in a straight line, because we have say few millimeters of length by widths available to you and you have to diffuse everything in that area only. So, the way a interconnect travels or a wire travels inside an IC, it may not always be in a straight line, but it may be in the form of loops, and when current flowing through these loops changes, the amount of magnetic field produced is also going to change. The orientation of this magnetic field is also going to be different. So, the value of inductance becomes more and more difficult to estimate, but it is going to exist, especially at very high frequency. So, this is particularly the origin of inductance inside an integrated circuit. So, whenever the current flowing through the interconnects changes, especially at high frequencies, it is going to produce a magnetic field which is going to oppose that flow of current through it by generating a voltage, and that voltage is proportional to the rate of change of current, the proportionality constant being the inductance. Okay. So, how we calculate? There are different models available, there are different mathematical tools available. Okay. Generally, resistance and capacitance can be available on board on an IC. Okay. So, you can have a resistance and a capacitance as in the form of SOC on the on system, but inductance may or may not have that kind of liberty. Inductance may be available on chip or it may be connected separately, but the way we connect or way we calculate, how we calculate inductance, we are dependent upon the length and width located at a height. Okay. So, we have defined a length L, we have defined a width W located at a height h above the ground plane. So, the inductance can be modeled as L mu naught by 2 pi natural log of 8 h by W plus W by 4 h. So, we have given the symbols. L is the length of the interconnect, W is the width, h is the height above the ground plane. Okay. Mu naught stands for magnetic permeability of free space, which has a fixed value of 4 pi into 10 to the power minus 7 Henry per meter. The above equation has a small assumption that the width is quite smaller as compared to the height, okay, and the thickness is negligible. Now, typically for interconnects, the value of inductance we are looking at is 0.15 to 1.5 picohenry per micrometer. This is more of a guideline. Okay. Depending upon how much is the proximity of an interconnect with either the supply line or the ground line. Okay. And what is the impact of this inductance in an interconnect? You can use it for a few things to calculate. One important parameter is known as flight time, okay, or you can also define it broadly as flight time across an interconnect. This is basically the time it takes for a signal to travel or traverse an interconnect. Okay. By interconnect, we should be clear by now that we are talking about piece of copper wires traveling inside an integrated circuit, connecting diffused in such a way that they are connecting one circuit to another. It might be implementing some logic, it might be implementing some switching application. Okay. So, these interconnects have that objective. So, if you know the inductance along with the capacitance, okay, capacitance we have discussed in one of the previous lectures. So, if you know the inductance, if you know the capacitance associated with an interconnect, you can calculate the time it takes for a signal to travel across one interconnect, okay, and that is given by T equal to L square root L multiplied by C. Okay. So, where L is the length of the interconnect and L and C are the inductance and capacitance per unit length respectively. Another parameter which you can estimate if you have knowledge about the inductance and capacitance associated with an interconnect is known as the velocity by which it traveling by which the signal is traveling across an interconnect. Okay. So, in the first parameter we have calculated the time, in the second we are basically calculating the signal velocity, the rate or the velocity at which the signal is traveling across an interconnect, and it is given by V, denoted by V and written as V equal to 1 over square root of L C, okay, and it can also be written as 1 over square root of epsilon oxide and mu naught. Mu naught we have seen on the previous slide is the magnetic permeability of the free space, and epsilon ox is the dielectric permittivity of the gate oxide. So, depending upon the material you use for the gate oxide for MOSFETs, it is going to have certain dielectric constant, and that is going to decide the value of its permittivity. Okay. Now, third parameter which is affected by inductance is known as inductive crosstalk. Okay. So, these are two already known special or separate words, inductive and crosstalk. Okay. as we have seen that the density in the inside an integrated circuit is very high, and because of this high density, the current flowing through one interconnect might influence the amount of current flowing through another interconnect. And since presence of this current affects the magnetic field generated through the interconnect, these fields can interact with each other. Okay. They can interact in terms of their magnitude, in terms of their polarity. Okay. So, these different changing magnetic fields in turn can cause differences in the level of current in the other loops. Okay. So, signals on one wire can inductively couple onto another, and this is known as inductive crosstalk. This might enhance the signal, or this might reduce the level of current flowing in neighboring wires. Okay. So, these are some of the impacts which we have on the inductance. So, in addition to resistance and capacitance, which you might already know, we have introduced the concept of having inductance in interconnects inside an integrated circuit. The next topic which we will discuss today is known as skin effect. Okay. So, now skin effect also has its origin in the value of inductance only associated with a wire, right. So, by now it is clear that when we are passing current through an electric conductor, a magnetic field is being generated. That magnetic field is producing some voltage, a back EMF, which is opposing the current which originally produced this magnetic field. And because of this operation, the way the magnetic field is producing this back EMF is via a set of currents called eddy currents, and these currents tends to spread out. Okay. And when they spread out, they tend to push the bulk of the current towards the surface, and this also has another reason, that current tends to flow through a path of low impedance. And when we see any kind of a conductor, the conductor by itself can be considered as a material with concentric conductive elements. Okay. And because of this, the field or the flux which exists in the center tends to be very high, and it tends to spread out and reduce in magnitude. So, the amount of flux phi associated with a conductor tends to be concentrated more towards the center, and it reduces while we traverse towards the edges. And now, the inductance of this conductor is actually directly proportional to this phi. Okay. And because this inductance is directly proportional to the flux which is being produced inside the conductor, okay, the amount of inductance tends to be maximum in the core and quite less comparatively on the edges or on the surface. Because of this, the total impedance associated with any conductor tends to be lower at the surface and higher in the bulk or the core. And because of this, the total impedance associated with any electrical conductor tends to be lesser on the surface as compared to the center. Because of this, most of the current, especially at high frequencies, tends to be concentrated on the surface rather than in the center. And when we say surface, we can also consider it in a way that the current is concentrated more on the skin. Okay. That is why it is known as skin effect. Right. And at high frequencies, the inductive reactance, which is given by 2 pi f L, f is frequency and L is inductance. Okay. So, at high frequencies, this reactance tends to be very high. Okay. So, when the value of inductance increases or the value of frequency increases, you have higher inductive reactance. This also tends to enhance skin effect, and more current then begins to flow on the surface or on the skin of an electrical conductor. This entire phenomena is known as the skin effect. So, the effective depth to which charge carriers are basically present is actually very small. Okay. So, if you have if you see this small cross section of a conductor shown here with thickness T and width W, bulk of the current is actually flowing through a certain depth denoted by delta, okay. And this delta is basically known as the skin depth, okay. And defined as the depth at the surface up to which current is concentrated, okay, and given by the equation square root of 2 rho by omega mu. Rho is the resistivity of the material, mu is magnetic permeability of the dielectric, and omega is the frequency associated with the edges. Okay. And the frequency associated with the edges, omega, in the above formula can also be written as 2 pi divided by 8.65 TRF. TRF is your average rise and fall time, the time it takes for the signal to rise from 20% to 80% of its final value, or to fall from 80% to 20% of its final value. Okay. That time it takes is TRF. Okay. So, this is more about skin effect and skin depth. Let us take one example on calculating skin depth. So, if you are given a copper wire, okay, as you know, copper is now the most preferred metal for producing interconnects. Initially it used to be aluminum, now it has been replaced with copper for quite some time now. Okay. So, for a copper wire inside a chip or an IC, it is displaying 20 picosecond of edge rates. So, consider air as dielectric. So, the dielectric which separates different interconnects is nothing but air. Okay. Air, as you know, is a dielectric, and resistivity of copper is also given. Okay. So, the frequency associated with the edges as shown on the screen is omega equal to 2 pi divided by 8.65 rise and fall time, or the edge rates basically is given to you. So, substituting the values, you can get the value of edge frequency and the skin depth, the depth up to which the bulk of the current is flowing. Okay. So, if you subject this type of a copper wire or a copper interconnect to a very fast circuit where frequency is very high, okay, the depth up to which your current, majority of your current or bulk of your current is going to flow is given by this formula square root 2 rho by omega mu. Okay. So, you substitute the value of resistivity, you have already calculated the frequency, because we are considering air as dielectric, we just use the magnetic permeability of air. Okay. So, substituting all the values and doing the calculation, you get a value which is very close to 1 micron. Okay. So, does not matter how thick or how wide conductor you use in such a scenario, only a micron from the surface inside, only about a micron is going to have most of the current. Okay. So, most of the current is going to be carried within the first micrometer of this copper wire. Okay. So, this has also been actually been used, this whole phenomena of skin effect. It is not necessary that it is a negative effect. Okay. It might sound like that because all the current is concentrated only on the surface or the skin of the conductor, it might be some kind of a parasitic effect. No, it is true that there is a lot of concentration of current, okay, but this is something which you can also exploit to use in some applications. Okay. On the negative end, it does tend to increase the effective resistance, okay, because it is reducing the effective surface area of your conductor, because your current gets concentrated say few microns within the surface. So, the effective surface area tends to reduce, and since resistance is inversely related to area, it tends to increase the effective resistance. So, at high frequencies it can also produce attenuation. Okay. In the radio frequency area, you use various RF antennas or you use a lot of cables for transmitting RF signals. Okay. These antennas actually make use of skin effect by using what is known as a hollow copper tube. Okay. So, you are going to have some copper tubes and a majority of the area is going to be hollow inside. So, it is going to have hollow region inside it. That is because most of the current, because of skin effect, is going to be concentrated at the surface or only few microns within the surface. So, you are going to save a lot of cost on the material. Okay. So, you can use hollow wires. On the other hand, you can also use steel wires on the outside with copper cladding. Okay. So, steel enhances tensile strength, okay, and majority of current flows through the copper due to the skin effect. So, this is a better electrical conductor than using steel. So, in high frequency application, in order to reduce cost, you can use the skin effect. Okay. Now, we need to discuss something about RC models. Right. We have seen about resistances, we have seen about capacitance. Okay. Interconnect produces circuit delay due to its resistance, due to its capacitance. Okay. Now, with a lot of density of wires, it is sometimes difficult to quantify how much delay is being produced. So, we need some kind of models for it. One of the most simple model which we use for calculating RC time delay is known as the lumped RC model. Okay. So, what it basically does is that it gives one value of resistance and it gives one value of capacitance. Okay. So, entire resistance is averaged over and then entire capacitance is averaged over and you get one single value. So, the entire wire is represented by a single value of R and a single value of C. Okay. And it is assumed to be connected at the end of an ideal wire. An ideal wire is the one which does not have any resistance, which does not have any capacitance, no inductance, no delay. Okay. So, this model, this RC circuit, series RC circuit gets connected at the end of the ideal wire to calculate the delay. So, the resistance of the wire is calculated by a formula which is length L times the internal resistance or unit resistance of the wire or resistance of a wire of unit length. Similarly, you can describe C subscript I n t, which is capacitance of a wire of length unity. Okay. So, once you know these values, okay, multiplying it with the length of the actual wire provides you with the value of the wire of the resistance and the capacitance. In that case, the time delay introduced is the resistance of the driver plus the resistance of the wire, okay, added together multiplied with the capacitance of the wire. Based on this, once you have this tau RC time constant, you can calculate the 50% propagation delay, which is the time it takes for the signal when it appears at the input, okay, and when 50% of it appears at the output. Okay. So, that is the propagation delay. Using the same equation, the rise and fall times, how much time it takes for the signal to rise from 0 to 90% of its final value or to fall from 90% of its final value. Okay. So, these are some of the formulas you can use for calculating the delays, rise time, fall time using the simple lumped RC model. The second model is known as distributed RC model, which basically divides the wire into small segments of R and C, okay, resistance and capacitance. So, if you have a large length of wire, okay, especially for longer wires, lumped model becomes less accurate. So, you break down the wire into small segments, where each segment has a certain resistance, certain capacitance, and each segment is connected in series. Okay. So, suppose each segment has an incremental length of delta L, then each segment would have a certain resistance multiplied R, unit resistance multiplied by delta L and unit capacitance multiplied by delta L. And then the total delay of the wire is estimated something using called the Elmore delay model, which is nothing but once you have divided the wire into small segments of resistance and capacitance. Okay. In that case, you keep adding the resistances and multiply with the capacitance at the end of each branch. So, you start from the source, you end at the load, you keep adding the resistances and keep multiplying with the capacitance at the end of the branch. Okay. So, small mathematical analysis gives us the total delay associated with that interconnect using with this equation. Okay. Finally, you arrive with something like half of L square, where L is the length, R and C, these are basically the unit resistances and unit capacitances. Okay. For unit length, if I substitute L with 1, I am going to get half of R wire and C wire. Okay. So, resistance of the wire, entire wire multiplied by the capacitance of the wire, half of that. Okay. So, that is the theoretical value. Practical analysis has actually shown that this Elmore delay is somewhere around 0.38 times the wire resistance and the wire capacitance. Okay. So, you can see that the delay of a wire is a quadratic function of its length. That is why the distributed RC model is more valid for longer wires, okay, whereas for shorter wires you can do away with the lumped RC model. Okay. So, finally, the distributed RC model uses 3 different types of topologies. These are called L model, pi model and T model, okay. But the basic method remains the same. You start with the resistance, keep adding them and multiply with the capacitance at the end of each branch. Okay. So, with this we end today's lecture. We have covered topics like inductance, skin effect and given an introductory analysis of RC models based with interconnects and how you use with these models for calculating the delay associated with wires. Okay. Thank you.